Hello. I'll start with an outline of what we'll talk about today, starting with our motivation for the problem, followed by the steps we take to build our formulation. After that, we'll talk about what solution methods we use to improve performance of the formulation, and then we'll finish with some computational results. First, you're probably familiar with the concept of ride sharing. The main idea is that a rider will go to a platform such as Uber or Lyft and ask to be matched with an available driver to take them wherever they need to go. Drivers can decide when they want to participate with the platform, but for the most part, they don't get to decide what requests they're going to fulfill. Namely, they don't usually get to see the destination of the request or how much they'll be paid until after they accept the request. And also, if they refuse too many requests, the platform may stop sending them offers. Similarly, in the current literature, driver autonomy is usually limited. They are usually, in most models, they're assumed to accept whatever request they're assigned to. As for compensation, usually the driver receives perhaps some function of what the trip length is, or perhaps a fixed percent of the fare, or something like that. So our contribution is a model that can create both personalized menus and personalized compensation offers to drivers who are assumed to make stochastic selections. This graphic shows an overview of the process that we're optimizing. First, the platform sends out a menu to each available driver containing current requests along with a compensation offer. After that, the drivers for each item in their menu will either accept or reject that request. And then after that feedback is received, the platform will send out a final recourse assignment. And so these platform decisions want to maximize the income from the fare collected minus the cost paid to drivers, and also maximize the number of matches. As for what the drivers will accept, we assume that there's this utility parameter, util ij, that driver j will accept the request I if it's in their menu, and if utility ij is greater than 0. The problem is that the platform doesn't have perfect knowledge of what this utility parameter value is. So we model it as a random variable, specifically a Bernoulli random variable, because either we have a success, or as in the driver accepts, or we have a failure, they reject. And so we model the probability that they accept as the parameter Pij. With this accepting and rejecting of requests, there's a number of possible outcomes you could have between all the different drivers and requests. So we identify information about the driver's selections for each request and each driver as a scenario. And so we have two example scenarios at the top, where a 1 represents an accept and a 0 is a reject. And you can see by the orange values that these two scenarios have some different outcomes for driver selections. So the method that we take inspiration from is the sample average approximation, which will take a sample set of these scenarios, only a sample because there's a huge number of total scenarios. But within that sample, you look at what the optimal recourse assignment is for each driver scenario and optimize over the expected performance of your decisions. We, however, cannot use sample average approximation exactly, because these scenarios should be generated beforehand and then inputted into your optimization program. We can't do that because driver behavior is endogenous. That is, we assume that the utility would depend on how much the driver is paid, which is also a variable in our formulation. And that means that both the probability Pij and the driver selections are variable. This is our list of variables that we use in the formulation. First, the platform has to send out the compensation and the menu. The menu is X, compensation is comp, and then P double dot is our variable representation of the parameter P. Next, driver selections are modeled with Y, and then the recourse assignment is represented by V. We have a handful of constraints that I won't go through individually, but these just ensure that the assignment and the menu are a valid assignment and menu. Next, we have to make constraints so that our P double dot variable accurately captures Pij and has the correct value. We assume that Pij follows this orange curve that's piecewise linear and depends on the compensation. And for P double dot, we do not model the second breakpoint because it's okay in the formulation if P double dot exceeds 1, and it keeps things simpler. We do model the first breakpoint by breaking comp ij into two non-negative components, Tij and Uij. And the compensation is the sum of these two variables, and they are also bound by a complementarity constraint. That is, U can't be positive unless Tij is at its maximum value alpha. But if we include this complementarity and the range for each variable, we can capture P double dot as the green line using the linear constraint shown below. Next, we have to capture how driver selections, the Ys, will interact with P double dot. These selections would ideally be a Bernoulli random process, but that's pretty much impossible to capture with linear constraints. And so the best that we can do is, given our sample size, which we know, and if we calculate P double dot, we should be able to calculate how many successes, i.e. how many accepts across the scenarios that driver and request would have. And so that's given by the equation there. We do go a little bit further though, because we only constrain the number of successes. And that means that the solver can kind of strategically allocate which scenarios the successes happen in so that there's always a good recourse assignment. So to counteract that, we require the solver to pay a premium. That is, they have to offer a higher compensation for however much driver participation they want to use in the solution and their recourse assignment. Putting this all together, along with constraint 9, which is a minimum compensation constraint so that the driver receives at least some certain amount of money, we have our nonlinear compensation formulation. There are two sources of nonlinearity. Number one, the objective value or function has a product of variables, and we also have the complementarity constraint 10. Fortunately, we can deal with these without too much hassle. It turns out if you replace the variable t with just its upper bound, the parameter alpha, the quality of solution is not compromised and the complementarity constraint is no longer needed. And as for the variable product in the objective, one of the variables being multiplied is binary, so we can just use McCormick inequalities and introduce a new variable phi that represents the variable product. With these changes, we have our linear compensation formulation, or LCF, given below. LCF on its own does not perform competitively with existing methods, and so we use a few solution methods to reduce the number of decisions that the formulation has to make at any one time. So the first thing we do is we split up the formulation into two steps. First, we fix the compensation to some default fixed scheme and find an optimal menu using SLSF, which is a method we'd have designed previously. And then once we have a menu from SLSF, we plug it in as a fixed parameter to LCF and then get the compensation from there. In addition, we have variable scenarios for driver selection in LCF. It also helps to add some population of randomly generated fixed scenarios using that same fixed compensation used to get the menu. And this enforces that at least some variables do follow a truly random process. And so it reduces that amount of strategic allocation that I mentioned earlier. And lastly, we take our two-step method of fixing compensation, get menu, fix menu, get compensation, and we iterate back and forth a number of times. And this improves the quality of the solution as well. However, it doesn't improve monotonically with each iteration, and so we do small performance tests after each iteration to decide which iteration had the best solution that we will return. And this method is called LCF IT for iterative. We do a performance analysis overall of each solution because the objective value returned with the solution is usually overfitted, and so it has a positive bias. So to create an unbiased estimate, what we do is we create a large sample of random scenarios and calculate the recourse assignment for each scenario and the corresponding objective, and then take the weighted average of those objective values. To run our problems, we need driver and rider data, which we get from the Chicago Regional Transportation Network. We take a subgraph of the network, and there are demands between each pair of nodes, which we generate rider and driver trips. And then the ARC information also has the distance and the time needed to traverse any links, so we can calculate trip length. We ran 100 problems, each with 20 driver trips and 20 request trips. And the graph on the left shows what the compensations were across these problems. So the yellow line represents the minimum allowed compensation, the orange is the maximum, and then the green is the 45-degree line. So we can see by the dots that while they are mostly in the lower half of the allowed compensation range, most of them are above the minimum, and a handful are even at the maximum compensation offer. The graph on the right shows the distribution of a driver's expected income, both for our fixed compensation method, SLSF in blue, and then the orange is our LCF IT method. So these distributions are similar. The main difference is that you can see in the $0 to $3 bracket, there's a much larger number of SLSF drivers receiving that amount, where for LCF and the variable compensation, those drivers, you can see by the orange peeking over, are receiving a higher income instead. Overall, we compared our new method along with our fixed compensation method to two heuristics, where these heuristics, each driver receives 5 items, and then the menus are optimized to either minimize driver wait time, or rider wait time, which is close 5, or the likelihood that the drivers will accept, which is like 5. We can see that as for the objective, higher is better because we're maximizing. LCFIT is about 2% better than SLSF, and even more than the heuristics. The profit is slightly lower, but it makes up for that with a higher expected driver income, which is the next column, and a significantly lower number of unmatched requests. The trade-off, however, is that it does take significantly longer to run compared to the other methods. In conclusion, we were able to make a method that is initially nonlinear, that makes compensations and menus to send to drivers. We're able to linearize this method, and then we're able to improve it by adding solution methods. And this final method, LCFIT, offers an improvement in objective and in driver income, as well as lowering the number of unmatched requests. These are the references I used in the literature section. And thanks for joining me. Have a great day.